Here are the primary types of solar panels. We have polycrystalline. They're very common, and they have an 8 to 16% efficiency. Single crystal, which are also rigid panels, very common use. And we have amorphous, inflexible, or rigid design, lower efficiency, but a very interesting design, and the new thin film or printed-on solar panels, which have up to a 20% efficiency. Polycrystalline panels like these are made from silicon, which is not one solid ingot when it's fabricated. The panels are rigid and of very high quality. These are in common use and have efficiencies of about 8 to 16%. Single crystal or monocrystalline panels are panels which are made where the material is actually formed as a single ingot or piece. These are also high quality and have efficiencies up to 18%. Amorphous panels are made normally by creating the PV material on a backplane, in this case glass. These are normally lower in cost and may have a shorter ultimate service life. They are in common use and also come in flexible forms. Thin film photovoltaics are the latest technology. They are solar panels made in a continuous manufacturing process using only 1/10 the silicon of traditional panels. The cost reductions are a result of the method of manufacture and less materials being used. They're not commonly available yet. They can also be fabricated as a coating to an existing structure. Flexible amorphous panels actually can be bent, and they're primarily used in maritime and portable operation, and they're very costly. Now let's look at how the panels actually physically connect with the other components in the system. We're going to get technical on you here again, but the good thing is the chapter on batteries is the same as the chapter on solar panels. In other words, the way that they hook up in series and parallel is the same as batteries. So if you learn that pretty well, we're going to reinforce that here with the solar panel connections. Let's say we have three 12-volt and 1-amp panels, and we connect them in series by taking the plus of one, connecting it to the minus of the other. If they're 12-volt 1-amp, this would give us 36 volts, but still only at 1-amp output. If we take those same panels and connect them in parallel by putting all the pluses together of the panels and all the negatives together, we would then add up the current to have 3 amps total output at still 12 volts. Here's a real-world example. If I have 4 panels that are 21-volt panels at 7 amps, and I have a 24-volt battery bank, I can add 2 of the panels in series to give me 42 volts at 7 amps, and then the other 2 in series, giving me 42 volts at 7 amps, but then I parallel those 2 sets, and then it adds up their current. So I have 42 volts now at 14 amps. We're doing this, of course, to give us a little bit more voltage than our battery bank requires. Of course, first, you're going to have to decide what kind of voltage you need on the output of your panel array. And you have several criteria to consider. Number one is, what is your voltage on the battery bank? Because your PV array output has to be higher in voltage than your battery bank. Number two, how far is the photovoltaic array from the batteries? If you're more than 50 feet, you should probably already be running a 24-volt battery system, allowing you to run more voltage coming in from the array and overcome that longer line loss. And third, what's the highest voltage that your charge controller can handle? Your controller manual will show this. Let's first revisit the battery bank voltage decision. If you have a 12-volt battery bank, that's going to be because you need to use 12 volts for low voltage appliances like RV appliances or ham radio equipment, and the run to the inverter is going to be very short, 8-10 feet, something like that, because at the lower voltage we can't have a very far run. Now if you go to 24-volt battery system, which is a good place to be, that's because you don't need 12 volts in the house for anything, and your wire run to the inverter is going to be maybe 12 feet, 15 feet max. Or maybe you've got an over 50-foot run from the panels to the batteries. On a 48-volt system, that's where your distance to the inverter is going to be even further, but there is less of a selection of inverters at that 48-volt level. And number three, check your charge controller's manual for its maximum voltage input specification. Each charge controller has a maximum voltage input rating, and do not exceed this with the voltage coming from the panel array. you know that you must be higher in voltage from the panels than the battery voltage is in the battery bank. 50% higher is good, but if you go even higher, you'll start to lose a little efficiency in the charge controller. Remember, if your PV array has to be located more than 50 feet from the charge controller, you should select a slightly higher voltage output configuration and increase your wire gauge coming in from the panel array. The chart in your controller manual will give you the appropriate wire gauge. Here is what a typical wire gauge chart might look like. You've got the amps from the array on the left, you've got the wire gauge required on the top, and then you have the distances for a 24-volt battery system that you can go coming in from the panels to the charge controller. And these are maximum distances for less than a 2% energy loss. So boiled down, here's the guidelines. If you have a one-panel system, it goes directly to your charge controller. If you have two panels, you could wire it in series or parallel, depending on how far it's going to be from your panels into the charge controller and the other criteria. Same with three panels. They could be all in series or they could be all in parallel. If you have four panels, that very typical configuration of two in series, the other two in series, and then paralleling the two packs is one of the most common ways to wire those. You could wire them all four in a row, but you're going to be at a pretty high voltage level and incur a little bit of loss in the charge controller. It would still work fine. If you have more panels than that, you're going to simply add the number of panels in series to get the desired E or voltage that you want, and then clone those series packs and wire them in parallel. Thus, you're not going to buy an odd number of panels. You're going to buy the exact number of panels so that you're going to have as many as you need in series to get that desired voltage, and then duplicate that set of 2, 3, or 4 in series until your budget for solar panels is exhausted. So what type of panels should you get for a particular job? You can go and shop for the best value available when you're ready to buy, because the voltage and size are not terribly critical. We can wire up almost any type of panels to get your desired voltage output. Just go and shop for the best dollar per watt value in a physical size that you can easily mount where you will be placing the panels, and I would suggest do go for a known manufacturer. Now let's look at our actual physical wiring connections on the solar panels themselves. Up until recently, all panels came with connection boxes on the rear like this. You can see that the wires connect under the screw heads. The panels will show which are the positive and negative screws. Some have jumpers for configuring them for 12 volts or 24 volts. Follow the diagram in the box to set it for your desired voltage. Smaller panels may still come with a connection box like this. Here's a close-up of the wire connections. Notice that you just strip the end of the wire, loosen the screw head, and place it under the cap, and then tighten down. Don't over-tighten, just tighten enough to hold the wire in there. I'm using 2 wires in this situation just to double up on the copper and be sure I have very low loss between each of the panels. Recently, panels are coming with connection boxes like this. They're already pre-wired internally, and the wires come out to nice connectors just like this. It really makes it easy to snap connect one panel to the next by just pushing the connectors together. Here's the standard snap-together connectors that are going to come out of modern panels. They simply push together, and then you squeeze here to release them if you want to take it apart. If you're wiring panels in series, you're going to find that easy. Negative to positive, because these are negative and positive connectors, and just snap them together. But if you get to the point where you need to parallel a bank of 3 or 4 panels, well, how are you going to do that? Because you've got these genderized connectors. How you're going to do it is by buying an extension cord like this. You're going to buy a 20, 30-foot pre-made cable, which you can cut in half and then strip the ends and recombine them to make adapters for the plus and minus as needed. And here's the MC tool. You're going to need one of these to actually take connectors off. You actually insert it right into the side of the connector, and then that will allow you to release the connectors. The tool also has a few other uses, and one of the main ones is to tighten or release the end cap on the connectors. So let's run through this and state this clearly. We have a potential wiring problem when we're trying to wire in parallel because connectors are gendered with positive and negative. It isn't possible to connect 2 positives or 2 negatives from the same type of photovoltaic panel together. The connectors will not snap together. Luckily, the solution is easy when you buy these extra extension cables. So you cut two connectored extension cables in half, and each is going to have a connector on each end, a positive and negative. Now you can connect that pigtail to the panel's output connector, whatever gender it is, and use the other end as bare wire, so you can solder it together with other wires. Since you haven't come across this problem in real life yet, this may seem vague or strange, but you will come across this problem, and then this solution will seem very obvious. Here we have the classic 4-panel installation, where we have 2 in series, 2 in series, and then we're paralleling the 2 banks. Well, I've got 2 plus on the top I have to put together, and 2 minus on the bottom, but since they're the same panels, they have the same gender connectors on their negative and positive sides. So I've got to use my little pigtails I've cut in half so that I can use the opposite gender to connect to that panel, and then use the bare wire on the other end of that pigtail and solder it together. And that's how it'll work, and then those wires will come down and off the panel array. Instead of soldering them, you can also connect the bare wire ends of the pigtails in a combiner box at the array. This is a clean and reliable way to combine the wires from each set of panels. Now, the boxes are easy to use and usually provide fuses on each incoming line. Be sure that the fuses are the correct size for each panel set's output in amps. The combiner box is used to combine the wires from your array sets. So say you've designed your system for a certain voltage and you have 3 panels in a row in series and multiple sets of those. Well, you can take the plus and minus out on those and put them into the combiner box's plus and minus rail inputs. They're screw heads for the wires normally. Now, each one of these lines will have a fuse or maybe a circuit breaker, and you have to be sure that the output of each of your array sets, their current output, is correct for the fuse or circuit breaker that's in there. So about a 50% higher amperage rating on that fuse would be correct for each one of those sets of panels. And also you have to be sure that whatever voltage that does add up to, that those inputs on the combiner box can handle that level of voltage. And then on the bottom of the box, that's where you connect your larger wires and take them down and bring them into your battery box. When it's time to wire up your panels, do not connect the connectors while the sun is out between the panels. Panels are fully active and cannot be turned off unless you cover them up. So a little spark may occur which may damage the connector. So do your final connections in the evening or cover up the panels. Your solar panel frame itself, the aluminum frame, is not very strong. It needs to be supported by a substructure or another frame, and we'll talk about those types of frames later in the video, but handle them carefully before they're mounted. And the rear of the panels will always be sensitive to damage from sharp objects, so always protect the rear of the panels. Before we review, I'd like to go over some very typical panel configuration examples. The first example is simply 4 panels in series. This is where you've got a long run, you need a little bit higher voltage, and you let the charge controller convert all that power back into charging current for your batteries. So we're simply taking the plus of one and wiring it to the negative of the other. If you have snap connectors, this goes very, very quickly. Remember that your charge controller will have tables in the back of the manual that give you the correct wire gauge to come in from your array to the charge controller, considering the current output, the distance of your run, and the voltage of your system. In this configuration, remember not to get really, really close to the maximum input voltage your charge controller can handle, because winter to summer conditions will change and you want to leave yourself a good amount of elbow room. So say if you had 150 volt maximum input voltage on your charge controller, try not to go over about 100 or so. Leave about a third of elbow room at the top. And the next is a very common setup, the 2 packs in series and then paralleled. So here we have a 48 volt system, each pack bringing up 7 amps, and then when they're paralleled, it boosts the amperage up, so you have 48 volts at 14 amps. Remember, you're always designing for the voltage of the system. We could have 6 panels here and go ahead and add another 2 pack, or 8, and on and on. Your MPPT charge controller is going to change all that power into charging current for whatever battery pack voltage you've set. Your array voltage just always has to be over the battery bank voltage. And here's a 6-panel array. We've got 2 sets of 3 in series and then paralleled. So the wiring on the left and the wiring on the right is exactly the same. And then we're taking the plus off of one pack of 3, the plus off the other, and putting them in parallel, and the same with a negative, coming up with 72 volts at 14 amps in this case. Now, if we had a 120-foot run to the battery box, to have less than 2% loss in this system, we'd have to use 4-gauge wire. Don't skimp on the wires coming in, you'll lose power. And between the panels, 10 gauge is fine as long as the runs are short. And remember, when we're talking about estimating the output voltages for these different configurations, we are using an MPPT charge controller. An important hit point here, do not mix different panel types in the same array or installation, because each type has a different voltage and current outputs and can damage each other if connected together in the same array. Let's review Chapter 10. Panel types and electrical configuration. Photovoltaic panels are made in several different ways, and you may be using any of those types of panels. Photovoltaic panels come with different types of connections. Photovoltaic panels add up their volts, that's voltage, or E, in series wiring, and amps, or current, wired in parallel. You design a photovoltaic array for a certain voltage output. That design voltage is determined mainly by 3 criteria. For your panel array, don't go over about 3 times higher than your battery bank's voltage, or E. You can series and parallel panels in many different ways to obtain that design voltage, so the type of panel is not that critical. Going with the battery bank voltage higher than 12 volts is good because it allows you to run smaller wires coming in from the array and have the inverter a little bit further away from your battery bank. Modern large panels now use snap-together wiring, connectored wiring, so it's easier. Check your charge controller manual because it has charts that tell you the right gauge wire to use coming in from your panels. Handle your panels carefully before they are formally mounted because they're not that strong. And don't connect your panels to any of the other equipment with the sun out. You can connect between the panels, but that final connection to the charge controller, don't do that with the sun on the panels. And last, do not mix different panel types in the same installation.